use a biological detergent containing added but unspecified enzymes to do mysterious things to the clothes. As it happens, in both contexts, the enzyme's function is very similar, breaking down large chemical molecules into smaller bits that will wash away. People do not generally realize, however, that enzymes have much wider and more diverse roles, and that, in effect, they orchestrate the whole of life. Almost every chemical step in every living thing is guided by its own dedicated enzyme. Out of all the multitude of reactions that might theoretically be possible, enzymes select and guide the orderly sequences of reactions that we call metabolism, breaking down foodstuffs stepwise to give useful building blocks and reassembling them to make new biological molecules. Whether the sequence of reactions turns carbon dioxide, water and mineral salts from the soil into a tree, or brings about the emergence of a walking, talking human adult from a single fertilized cell, one after another the jigsaw pieces fall into place, unerringly steered by the team of enzymes. Enzymes harness the locked-up energy in some of our foodstuffs, or in the case of plants, the energy of sunlight, and redeploy that energy to drive a vast range of biological tasks. They switch processes on and off. They even make and interpret the DNA instructions. Finally, what makes enzymes themselves? The answer, of course, is enzymes. Nowadays, because enzymes literally control every biological process, many of our drugs are designed to knock out or damp down a particular enzyme activity. They are also increasingly used on their own, outside of their original biological context, as tools, for example in diagnostic kits, in chemical synthesis, in processing foodstuffs, leather, wood pulp, etc. We shall return to some of these important applications in later chapters. This, however, raises many questions. If we are going to talk about life in terms of sequences of chemical reactions, we need to ask whether living things carry out the kind of ordinary chemistry that we would recognize from our school science lessons. Can ordinary chemistry produce the seemingly special substances and structures characteristic of life? And at an even more basic level, what determines whether a chemical reaction can or does occur? How can enzymes influence these processes? How do they all fit together to make up something we can recognize as life? Beginnings and basics. The smallest unit of a substance is the molecule. Molecules may be combinations either of a single kind of atom or of two or more different kinds of atom. In the molecules of a pure substance, atoms are joined in precise numerical combination. In oxygen, for example, two oxygen atoms, each given the chemical symbol O, join together to make an oxygen molecule represented as O2. In black copper oxide, CuO, one atom of shiny copper, Cu, is combined with one atom of oxygen, O. Similarly, in every molecule of table salt, one atom of the metal sodium, Na, is combined with one atom of the gas chlorine, Cl, making sodium chloride, NaCl, which resembles neither sodium nor chlorine, fortunately, since both sodium and chlorine on their own would be decidedly dangerous substances to sprinkle on your food. The formula NaCl tells you the combining proportions, 1 to 1 in this case. In water molecules, the proportions are different since a single atom of the gas oxygen combines with two atoms, H, of the gas hydrogen to form water, H2O. This unequal recipe reflects the fact that oxygen has a higher combining power than hydrogen, a property that chemists refer to as valency. Hydrogen, chlorine, and sodium all have valencies of 1, whereas oxygen and copper have valencies of 2. These different combining powers relate to the underlying structure of the individual atoms, a level of complexity we need not delve into. And the simplest way to think about valency is as the number of arms each atom has to hold hands with other atoms. Oxygen, O, has 2 arms, but hydrogen, H, has only 1. In a chemical reaction, the atoms in the molecules involved rearrange into new combinations. Thus, in the specific example just mentioned, each atom from a molecule of oxygen, O2, can combine with 2 atoms of hydrogen. Therefore, for the arithmetic to work out correctly, the 2 O atoms in a single molecule of oxygen, O2, interact with the total of 4 H atoms.